Hello, AP Calculus AP students. Mr. Rickard here from Avon High School, and I want to welcome you all not only to a new school year, but to what likely could be your very first lesson that you have undergone or partaken of in this wonderful world of AP Calculus. And I really want to kind of lay the foundation here for what you're about to see in this first lesson. And I want you to think about what it would be like to have a superhuman power. And this superhuman power that I'm talking about is the ability to freeze time, to snap your finger and stop everything around you. Anything that was in motion would be perfectly still. Well, that's the secret power that calculus will provide. And we're going to talk a little bit about that power. Again, we're going to take a look at the very first lesson out of the course and exam description from the College Board AP Calculus course, and that's topic 1.1, Introducing Calculus, Can Change Occur at an Instant? And this is the lesson that I prepare for my students at Avon High School, just west of Indianapolis. So here's how I want you to think about this to kind of set the ball in motion here. The concept of average velocity is fairly intuitive. It's probably something that you have a little bit of understanding with if you took an algebra course, which I'm sure you have. Maybe even some of you have taken a physics course. Well, if I were to put this into like a real life perspective, the distance, say from my driveway in my town where I live, Avon, Indiana, is very strangely exactly 700 miles from the Florida-Alabama border. Trust me, I've driven it many, many times with my family going to spring break trips if we were going to visit the Florida Panhandle and going to Destin or going to Panama City or whatnot. And so right here you can see from the map, starting here at Avon and traveling through Louisville, Nashville, all the way down Birmingham, et cetera, Montgomery, right to the Florida-Alabama border, it is exactly 700 miles. Now, occasionally it might vary a little bit depending on how far I travel to get food or gas off of the interstate. And I would even remember playing games with my family about, hey, who's going to guess under 700 or over 700? You guys can pick the first restaurant that we decide to go to, which I guess if I'm driving, I have a lot of control, right? If everybody says, oh, we're going to get there at under 700 miles, I'll just go way off the beaten path to get gas or fast food or whatever on the way. So in any event, let's say that this 700 miles, I was able to drive there in exactly 10 hours. What would be my average velocity? Well, if you think about that, it's not really a calculus question, right? Maybe you are a little bit aware of this relationship. It says distance is equal to rate times time. And so in this particular case, the distance is 700 miles and the rate is something I'm trying to find. And the time I know is 10 hours. And if I divide the 10 hours over, R is going to be 700 over 10, which we know is going to reduce to 70, and the units would be miles on top, hours on the bottom, which we can just very affectionately call MPH, of course. Now, that's kind of interesting because what kind of an assumption could you make about my driving? Well, if you think about that, I think I was speeding, wasn't I? And the reason that you know that is that typically the speed limits or the maximum speed limits in most states on the interstate is 70 miles per hour. Let's just assume that that is the case through all of these states that I would be traveling. If that's the case, and this is my average rate, I certainly had to speed at some point. Now, why is that? Why would that be the case? Well, if my average was 70, that means that there's possibly times that I was going less or more than 70 miles per hour. For example, pulling out of my driveway, driving through my neighborhood, getting on an on-ramp, going through the fast food drive-through at Burger King. All of those things are things that I certainly was traveling at less than 70 miles an hour, let's hope. So because of those times that I was under 70, it's very likely that there's going to be some other times that I was over 70 to balance that out. And that's a really important idea in calculus that you're going to learn later called the mean value theorem. Just kind of laying the foundation right now for you. Let's go ahead and take a look at our first concrete example. Suppose we wanted to take a ball and drop it from the top story of the tallest building in the world, which is the Burj Khalifa, which is located in Dubai in the United Arab Emirates. And that building is 2,717 feet from the ground, where we're going to be climbing and then dropping the ball. The question asks to find the velocity after 5 seconds. And what that means is finding the velocity of that ball as it's falling right snap freeze time at the 5 seconds. That's the secret power that we're talking about. And unfortunately, we just don't quite have that power. Trust me, you're going to have that power in just a few short weeks. But I want to kind of build up to that power. I want to get our training undergoing here so that we're ready to take on that power. And so in order to make this happen, I'm going to take you back in history. How far back? Well, let's go back to right around 1600. There was an individual, his name was Galileo Galilei, one of the most renowned mathematicians, scientists in the world. In fact, he's in my list of my top 3 mathematicians. In fact, he's known by the name of Galileo, and you know you're pretty important when you go just by the first name, right? Think about all of those other famous mathematicians and artists and so forth that bared that same kind of notoriety, like Donatello, Michelangelo. Well, Galileo was very similar, kind of like Drake right now, right? Of course, I think that's Drake's middle name, but I think you get the idea. So what this guy did is he lived in this town called Pisa, which is in northern Italy. Perhaps you've heard of it because there's a building in Pisa that's kind of leaning, right? The Leaning Tower of Pisa. Well, that Leaning Tower of Pisa had been around for a while, and it was actually the tallest building in northern Italy at the time. And so what Galileo did is that he climbed to the top of that tower and he kept dropping objects. He dropped these rocks from that building, and with the help of an assistant, would time how long it would take for those rocks to hit the ground. And he just probably broke out his Apple Watch and just kind of timed it and got the accuracy down pretty. Wait a minute, no. Okay, probably not, right? No, of course he didn't have an Apple Watch, but he had what was called a water clock, which is this amazing device that could actually measure time to within tenths of seconds, very, very similar to our modern day stopwatches. It just drops water from one part of a container to another part, and you would just weigh the water to find out how much was there in each part, and boom, you were able to figure out what the time had elapsed. So anyway, he was able to do this over and over again, and he eventually came up with this idea that we use today. In this case, that the position of that rock, how far it's fallen, is just simply going to be 16 times the time that it's fallen squared. And that would tell you the distance that that rock has fallen. Now, I don't think he came up with this definition of 16 because he probably wasn't using the units of feet like we are now. And if you're a little bit abreast with some of the kinematic, I should say, equations from physics, you probably know that this is a negative 16 because objects are falling to the ground. And that would be the case if I was measuring position from the ground up. But instead, I want to measure how far the rock has fallen from the top of the tower. And therefore, I'm going to pull that negative out. Well, we have a problem with that. We can't really use this formula to figure out instantaneously how fast a rock has traveled. But we can outsmart the problem and get pretty close. And that's what we're going to do here by computing the average velocity over a very short time interval. So let's say if I go from time 5 to time 5.1. We could figure out what the average velocity is going to be there. And so if I want to do that, I could probably say, okay, if my time is 5, I'm going to use like the top half of this table here. What is the position at time 5? In other words, how far has this ball traveled at time 5? Well, I could just simply plug 5 in for the t. 16 times 25. You might think about, using a calculator if you need to. I know that that's going to be 400. I think I'm going to have to use a calculator for some of these other calculations, so kind of stand by there. And then if I want to do the same thing at time 5.1, I'm going to have to figure out, well, what is the position at time 5.1? Well, this is where I'm going to have to get a little help. So I'm going to run over to the calculator and I'm going to compute this to see what we've got. So here I go. I've got my trusty TI Inspire all loaded up and ready to go. That's the calculator that we use at my school. And what I'm going to do to maybe make things a little bit easier for me is I'm going to physically store the function s of t. I'm going to tend to use that equation over and over again. And so to store a function, all you would simply do is you would just type the name of the function, s, and then a parenthesis, left parenthesis, which is over here, of t. I'm making it look exactly like it looks on the page. I'll go to the right, and then this very important symbol is this piece right here above this math template button, which is what that is called, and below the delete button. And because it's in blue, you can kind of barely see that from the video, it's a secondary function accessed by the control button. Notice how the control button is blue. So you'll hit control and that math template button, and that brings up this colon equal, which is just going to tell the calculator to store this equation. There's about 3 other ways that you can store an equation on the TI Inspire. This is probably my favorite, and I think the one that takes the fewest button strokes. And so then I just type in 16, T, hit my square button, and then if I hit enter, the calculator will say done, which might make you think, well, done? It hasn't done anything. Well, trust me, it has, because now I can go in and type S, parenthesis 5.1, and it's going to spit out a decimal answer that is the value that we certainly want, 416.16. So returning to the document here, I can go ahead and say that that is my distance that the ball's traveled, which I think it makes sense that the ball would have traveled a little bit farther than 400 feet because it's been falling for another 1/10 of a second. Now, the average velocity is just simply going to be the change in position over the change in time. And so I can take these two things and subtract my S of 5.1, which is 416.16, minus the original distance 400, and I can put that over the difference of times, 5.1 minus 5. And if I do that, I'm going to get an answer of, well, let's see, can we do this without a calculator? We're going to try here. It's going to be 16.16 on top, and the denominator is 0.1. And then I think we can kind of play around with that and move the decimal over one space to the right. And I think we would get 161.6. And so that would be this average velocity, and it would be measured in feet per second of that ball falling between time 5 and time 5.1. But if you remember, our job was to figure out, well, how fast is it falling instantly at time 5? Well, in order to make this happen, we're going to have to compute some other estimates. In other words, we're going to have to find some times that are even closer to 5, much closer than 5.1. Maybe these are times that were a little bit too precise for Galileo's water clock to measure. But yet with our technology that we have now and the fact that we have a calculator that can find these very easily, maybe we can do this. And so what we're going to do is I'm going to pick some times here, like 5.01. and maybe even closer still, like 5.001, and then 5.0001. And I could have chosen a variety of these. I'm just trying to convey the idea that I'm getting closer and closer to 5. And so now I'm going to go ahead and find out what are these S of t values by returning to the calculator. All right, so let's do that. So we find ourselves back at the calculator. Notice I'm using a scratch pad on the TI Inspire. You can work in a document, that's perfectly fine. I'm not going to have a need to save this information, so I'll just leave it like this. So let's go ahead and compute S. Notice it's still going to remember our S, but now we're going to type in some different times like 5.01. And then maybe we'll try S of 5.001. And then how about that last one of 5.0001? And then notice how it gives me these 3 answers. Now, if you wanted to get those values a little bit quicker, there is another way to do this. And if you try to plug in more than one value in, you're going to want to use the such that symbol. And that's located in the Control Equal menu. And it's this vertical bar in the bottom right corner. That means such that. And then I can just say, okay, let's let t equal all 3 of these values, 5.01 all the way down to 5.0001. Now, here's the trick. These values you have to put in a certain grouping symbol called a brace. And the braces are found by going into the right parenthesis, noting what's above it, and hitting Control right parenthesis. And now I can type 5.01, comma, 5.001, comma, 5.0001. Basically separate as many values as you want to plug in with commas, and it'll give you those same exact answers. This time, of course, they're going to be arranged respective to the order that you had placed them in. Let's put these values in our table. So here we are back at our document. I'm going to go ahead and fill in those values that I just computed. So I had 401.602. These are all going to be measured in feet. These would be the distance that the object has fallen. Now notice that these actually get smaller as I write them in the table. And the reason is because my times are actually getting smaller, right? They're getting closer to that 5 seconds. So I'm kind of writing them in a different direction than how they would be appearing as the ball is dropping. So make sure that you're aware of that. And now I'm going to go ahead and compute my average values, my average velocity by using this expression. Let's go back to our table, or to our calculator, and I'll show you how you can do that. So here we are with our calculator once again, and I'm going to go ahead and define another function. I'm going to define that average velocity function. I'm going to give it a name, and I want to be very careful to not call it velocity or VEL or V, because I don't want us to get confused with that perhaps being our instantaneous velocity, because it's really still an average velocity, even though my time interval is very, very small. So I'm just going to make up a funny name. Are you ready? AVGV. That's what I'm going to call this. I just type all those letters together. How about I spell it correctly? And that's going to stand for average velocity at some time t. And then I can set that equivalent to, or colon equal to, the formula that we came up with, which is going to be the position, which, by the way, it still remembers that, the position at any time t minus the position at time 5, all divided by the time at t minus the time at 5. And note that this is just a slope formula, and so you could have reversed the order of the numerator as long as you reversed the order of the denominator, and it would still make sense. So now that's stored, and now the fun is going to begin, because I can find the average velocity at any of those times, like at 5.01. There we go. Let's try it again at 5.001. And another trick is if you don't want to type that all over again, you can cursor up twice, highlight what you're trying to compute, hit enter, and it just copies and pastes it. Only now you can edit it and change the numbers. And so there's my average velocity at 5.001, and then one more, the average velocity at 0.0001. And I get these values here. All right, well, let's take these guys and let's put them in the table and we'll wrap things up. And one last time in our notes, we compute these values. We just take them right from our calculator. We had 160.16, 160.016. We had 160. Well, the calculator here says 002 because it's likely that it rounded, but it's very, very likely that this was just 0016. And you can see how it just decided to round to the thousandths unit. And that's perfectly fine. We've got enough precision here. I think my point is probably going to be easy to make now. And that simply is, as we narrowed the gap from our time after t equal 5 to the time 5, which the closest that we got is right here, what would you say that this average velocity is approaching? And hopefully you're all thinking what I'm thinking, 160 feet per second. And you could probably surmise that that is the average velocity. I'm sorry, the instantaneous. Almost I blew it. The big reveal, it's the instant velocity. That's the superhuman power. Now, would there have been something that you could have done to this to get that 160 that's a lot faster? I don't know, just something that comes to mind here. What if you multiply the exponent and the number, 16, the coefficient? Wouldn't that be 32? And then let's just take that exponent and drop it by 1, t to the first. If we plug our 5 in for t, what's 32 times 5? I'll let you think about that. But this is just meant to be an introduction on how you can take average velocity and sort of tweak it and turn it into an instantaneous velocity, and to introduce one of the most important parts of all of calculus. It's going to be a long journey together. I hope you enjoy it just as much as I do. Stick around for the next video that's going to cover the conclusion of topic 1.1. In the meantime, keep studying, and we'll see you soon.